Hey there, welcome to another video on math problem solving. And today we're going to tackle something very different. How many factors does a number have? Is there a formula to figure this out? And why are we even interested? Um, the reason is life is all about this. If one has to live a good life, one needs to be good at this skill of pattern recognition. And nothing teaches you patterns more than number theory. And when you learn how to recognize patterns, that's a lateral skill that can be applied to many other fields, from physics to chess to philosophy to psychology. It's all about figuring out, identifying patterns, and problems such as this helps you understand pattern recognition better. So now that we have established firmly why we are doing this problem, let's get into it and how to do it. So let's assume for a minute we have no clue that even a formula exists for this. What would you go about doing? How would you go about doing it? So my suggestion would be to first take the first set of numbers. For example, let's assume we have one, sorry about two, three, four, five, six, seven, eight, nine, and we take one, 10, which is a two-digit. So what are the factors of one? Factors of one itself. So this is the list of factors, and this is the number of factors. So number of factors one. What about 2? It's 1 and 2. It's 2 factors. For 3, it's 1 and 3. It's 2 factors again. For 4, it is 1, 2, and 4. So it's 3 factors. For 5, it's 1 and 5. It's 2 factors. For 6, it is 1. It's 1, 2, 3, and 6. 4 factors. For 7, it's 1 and 7. Sorry, 2 factors. 8, it is 1, 2, 4, and 8. It's 4 factors. And 9 is 1, 3, and 3 factors. 10, it is 1, 2, 5, and which is 4 factors. So it's all over the place, right? Like you have, it's not increasing function. Suddenly it seems to dip again. Suddenly it rise again. So there's no pattern per se that when you look at it first attempt, there's no pattern. It seems like, okay, there's a pattern, let's think, but that's not always true with numbers because there'll always be some form of a hidden pattern. And uncovering that is what helps you build your pattern as well. All right, so what is going on here? So we've listed down the factors because we've not used any formula, we've just listed it down. This is where intelligence can help you solve or understand patterns a little better. So, what's intelligence? Our definition of intelligence is knowing similarities between differences and differences between similarities. So, look at all these number of factors. Let's look at this particular column. Let's focus here and see what's common. So, I have 2, which is definitely common between these 4 numbers. I also have 4, which is these numbers. I also have 3, which is common between 4 and 9, and there is also something here which is 1. What can I conclude from it? Now, the first conclusion that I can come with is 1 is uniquely the only number which has a single, because every other number is going to have 1 and itself at the least as the factor, as in the case with the prime numbers. So 2, 3, 5, and 7 are prime numbers and they have 2 factors, which means any number greater than 1 is definitely going to have at least 2 factors, because even in the case that it's a prime number like 97, it would still have 2 factors, 1 and 97. And that brings us to the second pattern, which is every prime number is going to have 2 factors, right? The moment it's a prime number, it has 2 factors. And there's something unique about it. Like if you look at it, all the numbers are even, but these numbers are odd. Why is that? And if you pay a little bit more attention, you'll realize that 1, 9, and 4 are perfect squares. So that you can think of the next set of factors, which is if a number is a perfect square, then it has an odd number of factors. So 1 is a perfect square, it is multiplied by itself, 1 times 1. 4 is 2 times 2, so it folds into itself, and that's the reason you have a single factor. Whereas for everything else, that's not the case. Let's take 10, for example. You can write it as 1 times 10, 2 times 5, and these are the 4 factors. But for 9, it is 1 times 9, well, it's 3 times itself. So you're double counting the 3 if you were to do it in the traditional sense. So which means 1 folds into itself, and therefore you get an odd number of factors. So let's test it out for 16. So I have 1 times 16, perfect, 2 times 8, perfect, and 4 times itself. And therefore it has 5, which is again an odd number of factors. Okay, I'm far away from getting a formula to this, but at least I've established a couple of patterns, which is also part of our reason for doing this. So 1 is the only number which has a single factor. All prime numbers have 2 factors. All perfect squares have an odd number of factors. And all even numbers end up having a lot of factors. Okay, so that's interesting. So you have 6 having 4 factors, 8 having 4 factors, 10 having 4 factors. And we'll extend this a little bit and ask, what about 12? So 12 is 1 and 12, 2 and 6, 3 and 4, and now 12 has 6 factors. Okay, so there seems to be an increasing trend that's visible for even numbers. Okay, so by that trend, can we think of 14? Okay, 1 and 14, 2 and 7, and there's only 4 here. Which means we look at it and say, okay, even numbers do seem to have more number of factors. However, that's also not an increasing trend, because you have 6, 8, and 10 having 4 factors. 12 suddenly gets 6 factors, and 14 goes back to 4. Okay, this gets really weird. So how do we actually figure this out? So let's focus into the process of finding out the factors. Let's look at 10 again. So 10 is 1 times 10, 2 times 5. Okay, let's do 12. 12 is 1 times 12, times 6, 3 times 4. So how does one break this up? And you can realize that, in fact, every number can be written as a product of prime factors. So prime factors is an interesting way to look at this. So for instance, 10 has 2 factors, 2 prime factors. It's 2 to the power 1 times 5 to the power 1. And 12 is 2 square times 3, the prime factor. So if I have prime factor, then I can essentially write every single factor here as some function of this. So for example, 1 can be written as 2 power 0. 2 is nothing but 2 power 1. 3 is nothing but 3 power 1. 4 is 2 square. 6 is 2 power 1 into 3 power. And 12 is 2 square into 3 power 1. So in other words, if you write down the prime factor, so I have 2 as a prime factor and 3 as a prime factor. And 2 can extend anywhere from 0 to 2. And 3 can extend from anywhere from 0 to 1. So in other words, 2 can be 2, 0, 1, 1, 0, 1, 2, and 3 can be 0 and 1. Now you can realize that every single factor here would be a product of this. So for instance, 2 power 0 into 3 power 0 gives you 1. 2 power 0 into 3 power 1 gives you 3. 2 power 1 times 3 power 0 gives you 2. 2 power 1 into 2 power 1 gives you 4. Sorry, 2 power 1 into 3 power 1 gives you 6. 2 power 2 into 3 power 0 gives you 4. And 2 square into 3 power 1 gives you 12. So in other words, if I list down the factors and I can find, anywhere between 2 to the power 0 till 2 to the power 2 and multiply it with other prime factors. So let's test this theory out. Let's take 16 and write down all the prime factors. So 16 is nothing but 2 to the power 4, which means I should be able to go from 0 till 4. So 16 should have 5 factors. This is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. These are the possible split and they're uniquely different. Let's take 20. 20 can be written as 2 square into 5 power 1. So 2 can range from 0, 1, 2 and 5 can range from 0 to 1. So it's very similar in nature to 6 to 12, where you can say that 0 connects to 0 and 1, 1 connects to 0 and 1, and 2 connects to 0 and 1. So in other words, whatever is that power, you just need to add 1 to it. That gives the number of connections that can be created with that as the base, that particular number as the base, and 5 would be 1 plus 1. So you would end up getting 3 times 2, which is 6 factors for 20. So by this extension, can we test it out for a larger number? Yes, definitely. So what is 100? 100 is nothing but 2 square into 5 square. So the base 2 can range from 0, 1, 2. The base 5 can range from 0, 1, 2. And if I can think of all possible combinations, this would be 3 times 3. So the power of 2 is 2, so 2 plus 1 is 3. The power of 5 is 2, which means 2 plus 1 is 3. This is a total of 9 factors. Now let's test if 100 actually has 9. The very first one is very easy. So it's 1 times 100. It's 2 times 50. It is 4. So it's 4 times 25. It is, what else can I say? 5 times 20, and then the next one itself. And therefore, I have 9. Okay. So from now on, if you were to come up with a really complex number, let's say a really, really large number, 225, all you have to do is prime factor 5. So that's 4. I do again, I end up getting 9. This is 3, 3 and 3 and 1. So now I know that 225 is nothing but 5 squared times 3. And therefore there should be, because 2 plus 1 is 3, 2 plus 1 here is 3, add this up. So this is your secret formula. When you look at any number, prime factorize it, look at the exponents of each prime factor, add 1 to it, multiply all of them, and boom, you've got the answer. I hope you found this video useful and informative. If so, please do like, share, and subscribe. And in the next 3 videos, we will be discussing how to use this particular formula to solve some more additional patterns